Have you ever looked up at a giant skyscraper or driven across a massive bridge and just thought, how? How does it not just crumble? Well, today, we're going to pull back the curtain on the invisible science that literally holds our world together.
Seriously, it can feel like magic, right? But it's not. The answer is in a field called mechanics of materials. This is the playbook that lets engineers see the invisible forces happening inside an object so they can design things that are truly built to last.
So to figure all this out, engineers have to speak a very specific language. And really, it all comes down to two key words: stress and strain. If you get these two concepts, you've got the foundation for understanding how anything, and I mean anything, behaves when you push it, pull it, or twist it.
All right, first up is normal stress. Just imagine you're pulling on a rubber band. Stress is basically the force that's fighting back inside that rubber band, all packed into its tiny area. The formula for it, sigma equals P over A, is actually super simple. It's just the force, the P, divided by the area, the A, it's acting on. So really, it's all about how concentrated that push or pull is.
Okay, so if stress is the hidden cause, strain is the effect you can actually see. You pull on that rubber band and, well, it stretches. Strain is just the measurement of that stretch compared to how long it was to begin with. It's the physical proof that the material is feeling the stress.
But here's the thing. Not all stress is a straightforward push or pull. I mean, that's what we call normal stress. But what about a force that tries to slice something? Kind of like scissors cutting paper. That's a totally different beast. That's called shear stress. So you've got one force trying to pull things apart and another trying to make its insides slide past each other. And engineers have to think about all of it. You've got your basic push-pull, what we call axial stress. You've got that slicing action, or direct shear. And then you get into the more complex stuff, like the bending you see in a diving board and the twisting action we call torsion. Every single one has to be calculated to keep things safe.
Now here's where it gets really powerful. Engineers can actually predict these changes with incredible accuracy. This formula is like a recipe. It tells you that how much something stretches is just a mix of the load you put on it, its original length, its area, and the special value E, which is just a number for how stiff the material is. You can know exactly how it'll deform before it ever happens.
And get this, it's not just about big, heavy loads. Even the weather can be a huge force. Think about a steel beam in a bridge on a hot summer day. It wants to expand, right? But it's bolted down. It can't. That internal struggle creates what's called thermal stress. It's another one of those critical, invisible forces that has to be part of every design.
Okay, let's level up. We've got the basics down. Push, pull, slice. But you know, in the real world, things are way messier. Forces love to team up to create much tougher problems for engineers, like bending and twisting. Let's start with torsion. The absolute best way to picture this is wringing out a wet towel. You're applying a twisting force, or torque, along its whole length. You see this everywhere, from the drive shaft in your car to the propeller on a plane. They all have to be designed to handle that constant twisting. And just like for stretching, you know there's a rulebook for twisting. This formula basically tells engineers exactly how much of that internal slicing, that shear stress, is happening at any point inside a shaft. And what it reveals is pretty cool. The stress is zero right at the center, but it's at its absolute maximum on the outside surface. And that's critical, because that's exactly where a crack would start.
Now for bending. Just picture a bookshelf loaded up with way too many books. It's sagging in the middle. Well, something really fascinating is going on inside that shelf. The very top surface is getting squished together. That's compression. At the exact same time, the bottom surface is getting stretched apart. That's tension. It's like a tiny war between two opposite forces inside the same object.
So how on earth do you design for that? Well, you use the flexure formula. This thing is a game changer. It lets an engineer figure out the stress anywhere in that bookshelf. It allows them to pinpoint the exact spots where the squishing and stretching are worst, so they can make sure it's strong enough right where it needs to be.
Okay, this is all fantastic in theory, but the real magic is seeing how these rules are used to design the actual parts that make our world work. So let's see how all this math and science turns into real objects we depend on every single day.
And I mean, the applications are literally everywhere. Every spinning shaft, every single beam holding up a floor, every gear in a machine, even the tiny welds and bolts that hold the whole thing together, every one of them is designed using these exact principles of stress, strain, bending, and torsion.
You know what? Let's zoom in on something we all take for granted. The humble bolt.
It looks so simple, but really it's a tiny masterpiece of engineering. Even the shape of its threads is the result of incredibly careful calculations, all designed to manage force.
It's a perfect example of form following function. You've got square threads, which are great for transmitting power efficiently. Then there are Acme threads. They're a bit stronger and easier to make. And then you have these cool buttress threads, which are designed to handle huge forces, but only from one direction. The shape itself is the solution.
So let me ask you a quick question. If you take a standard bolt with its smooth body and threaded end, and you pull on it until it breaks, where do you think it's going to snap?
Yep, it's gonna break right at the threads. And the reason is actually pretty simple. There's just less metal there. That same pulling force gets concentrated into a smaller area, which means the internal stress skyrockets. Engineers have a name for this, stress concentration. And it's basically a giant red flag that says, I'm gonna break here.
So how do you fix this weak spot? Well, the solution is beautifully counterintuitive, and I love it. To make the bolt stronger, you actually remove material from the stronger part. I know it sounds nuts, but by trimming down the smooth part of the body so it's as thin as the threaded part, you get rid of that single weak point. Now, the stress is spread out evenly along the whole bolt, which makes the entire thing way tougher and better at handling shock.
And really, that one little example of the bolt tells the whole story. This is the invisible foundation of knowledge that makes almost everything we build and use safe, efficient, and reliable.
And that's the ultimate goal, right? It's not just about making things that don't break. It's about deeply understanding these forces so you can create designs that are also efficient, using just the right amount of material in just the right places, so they can be trusted to work day in and day out.
So we've come full circle. The answer to how that bridge stands or how that airplane flies, it all lies in mastering this invisible world. From the chair you're sitting in to the most advanced spacecraft, everything works because an engineer understood, predicted, and designed for the stresses and strains it would have to face.
And that leaves us with one last thought. As we invent incredible new materials and try to build things that are taller, faster, and more complex than ever before, the challenges are only going to get bigger. But the fundamental language of stress and strain, these timeless rules of mechanics, they're going to be the guide that lets us build that future safely.